Welcome back. So let's see the decision boundary using the Stanford animation or the Stanford demo we discussed in the last lesson. So let's go here. As you can see, this is the K nearest neighbors demo, and this interactive demo lets you explore the K nearest neighbors algorithm for classification. Each point in the plane is colored with the class that would be assigned to it using the K nearest neighbors algorithm. Points for which the K nearest neighbor algorithm results in a tie are colored white. So if we have any regions that are white in this plane, then this means that we have a tie here. And of course, we can move points around by clicking and dragging, right? So we can change the point's position, and as you can see, based on this, the decision boundary changes, right? So as you can see, we can change the metric. So we can use the L2 metric or the L1 metric. So the L2 is the Euclidean distance. The L1 is the Manhattan distance. And in the next lesson, we will understand the difference between Manhattan and Euclidean distance. But if we change the metric from here, you will see that the decision boundaries also change. Okay? And we can also change the number of classes, and we can change the number of points, and we can change the number of neighbors. If we increase the number of neighbors, right, if we have 2, as you can see, we have many regions that are resulting in a tie. If we make it 4, we have also many regions with ties. If we make it 6, then there is also many regions with ties. But if we make the number of neighbors 3 or 5 or 7, as you can notice, the ties regions are much smaller. Why? Because if we have an even number of neighbors, if we have 2 neighbors, for example, in this region, right, in this region here, if we have a point here, then the first nearest neighbor is this one, and the second nearest neighbor is this one, right? So when we go to the majority voting, we will have one from this class and another one from this class. So we will have a tie. If we have 4, we also have a tie here, because the 2 first nearest neighbors are these ones, and then we have the 3rd and 4th nearest neighbors are these ones, right? So this will also result in a tie. So it's better to choose the number of neighbors, an odd number, because this will result in a smaller number of ties. Okay, this is one thing. The other thing that we can notice from here is that this point, as you can see this point, we can say that this point is an outlier, right? So this point doesn't really represent our data. But if we have the number of neighbors to be 1, as you can see, all the points, all the training points are classified 100% correctly, right? So as you can see, we have a region like this here. But this doesn't really make sense, right? So let's just remove this and put it here, right? And let's take a red point from here and put it here. By just looking at this graph, we can be 100% sure that this point should be removed, right? But if we didn't remove it and make the number of neighbors 1, then any point here will be classified as red. But this doesn't really make any sense. So we should increase the number of neighbors. So if we increase the number of neighbors, as you can see, if we increase the number of neighbors to be 3, then this whole region will be green and this whole region will be blue. Okay, and this makes much more sense. Although this point is misclassified in the training, so we'll have an error from this point, but the decision boundary, the whole decision boundary, is much better for generalization, right? For the test data. So sometimes it's better to decrease the training accuracy as a trade-off increasing the testing accuracy or the validation accuracy. And this is the case here. So I will leave this demo in the resources. It's free. You can check it. It's from Stanford. It's top notch. And you can try changing the number of neighbors, try changing the number of points, the number of classes, the metric, and make your own notes on this. And you can ask me in the Q&A or send me a DM if you have any question about this demo. Okay, so in the next lesson, we will understand the difference between the Euclidean distance and the Manhattan distance and when should we use each of them. So let's go.